Okay, this is the test for review for the multiple choice questions, and um, I will just let you guys know I am saving you because I just recorded this once and it was 22 minutes long, and I said, okay, forget it. I'm not doing a 22-minute long review for multiple choice questions. Okay, so I'm going to try to be real quick here. So, our first few questions are all about parallel wires. So I'm just going to draw two parallel wires with an I1, an I2, and then this, of course, could be going in either direction. This could be going in either direction. But one way or another, the force on them is going to be I, and specifically, and we're going to go ahead and integrate over this whole length, so it's going to end up being IL cross B, but what is B? B is just going to be mu 0 over 2 pi r, distance between them, and let's go ahead and say this is I1 and this is I2. If we were looking for the force from wire 2 on wire 1, we would just, wire 1 on wire 2, we would just flip these two around. Okay. And what's the direction of this going to be? Well, the direction is going to be, we're either going to have a B, oh man, I don't know how this is going to look to you guys. I think it's going to look like I'm drawing this backwards. It's a B that is curling out this way, which would be going like that. I'm drawing it backwards for me, and I think that's forwards for you. So B is either going to go that way or it's going to go this way. But one way or another, then this current is either, the force here is either going to go this way or this way. Okay, so that's the setup for all of these. So now the question is, they are separated by distance 10 centimeters, no external forces acting. You suddenly see them move towards each other. What can you say? They started carrying no current flowed in both. No, you can't say that because they could have started carrying some current and then they just increased the amount of current. They started carrying current and then current stopped in both. No, you can't say that because they could have been carrying current that pushed them apart, and then when that stopped, it brought them in, but that's not necessarily what happened. They started carrying current, then current increased in both. No, you can't say that either. You don't have enough information to say. So, not enough information to say for number one. Number two, same two wires. They start out carrying no current. You observe them suddenly move towards each other. What can you say? One wire now carries twice as much current as the other. Can you distinguish that by this equation? No. You can't tell what this is this is the force. You cannot tell from this whether it's I1 or I2 what their relative magnitudes are. Each wire contains the same amount of current. Nope, you can't say that either for the same reason. They carry current in the same direction. That you can say because they're either going to carry current in the same direction or opposite direction, and when you work through the right-hand rule, you will see that the only way for them to attract one another is if they're carrying current in the same direction. That's C. For the same two wires as the end of the previous question, the current in wire 1 doubles. What can you say about the force between the two wires? Well, first of all, the force of wire 1, if this is our initial force, and we now have twice as much I1, our force just gets twice as big. So the force of wire 1 on wire 2 is going to double. Well, this is actually backwards, right? The B1 would have I1 over here and I2 over here. But one way or another, that 2 still comes out here. So force of wire 1 on wire 2 doubles. The force of wire 2 on wire 1 doubles for exactly the same reason. Well, mathematically, it's the same mathematical reason. Physically, it's just because the force depends upon both the amount of moving charge and the strength of the magnetic field. The magnetic field of wire 1 doubles. Well, what is the magnetic field of wire 1? Mu 0 I1 over 2 pi r, whatever r happens to be. And what happens if you double this current? Sure enough, you just put a 2 out in front. So the answer is all of the above. Okay, number 4. For the same two wires, assume they're left in the state described at the end of the previous question. A charged particle zips right between the two wires, traveling perpendicular to the plane of the wires. What happens just as it's in the plane of the wires? So here is where our charged particle is it's either going to go this way or it's going to go this way, but it's traveling in this direction. Well, what is our magnetic field here? Our magnetic field in this plane is also, let's see, no, we don't know. It's also either this way or this way is the magnetic field. And so the magnetic field and the velocity are either parallel to one another or anti-parallel to one another right in this plane. One way or another, when you look at QV cross B, what you are going to get, VBQ, VB sine theta, the sine theta is going to be equal to 0, so this force is going to be equal to 0. Well, if the force is going to be equal to 0, let's see, where are we? There we are. Then what does that mean? It means there's no acceleration. If there's no acceleration, that means the velocity is not changing. So the answer is its velocity doesn't change. All right, now we're done with these two wires. Loop of wire carrying current I is placed in a uniform magnetic field B0. The magnetic field vector is not in the plane of the loop. What happens? So I've got some current loop like this, carrying a current I. I've got some magnetic field. Yeah, I'm just going to draw it like this. It's just not in this plane, which means basically there is, well, I'll just leave it at that. Yeah, what it means is there is some finite angle between the, some finite angle not equal to 90 degrees between the magnetic moment of this and the magnetic field that exists. So the magnetic moment of this is going to be either out this way or out down that way, the magnetic moment of this loop. And so what is the energy of this? The energy equals minus mu dot B. Well, what is that? That is just minus mu B cosine theta. And I'm sorry. No, that is right. Whew. I'm panicking for a moment. So mu B cosine theta, the answer, what is this loop going to want to do? It's going to want to make this energy a minimum. To make this a minimum, that means we want cosine theta to be maximum. So that means this loop is going to rotate until its magnetic field is lined up with the existing magnetic field. That's what it's going to want to do. So that is, the loop rotates so its magnetic field is parallel to B0. All right, two oppositely charged particles enter a region of constant magnetic field, both with velocities perpendicular to the magnetic field. So here's the magnetic field, and the magnetic field is, yeah, I'll just draw it this way. Let's say I believe that for you is going to look like it's going like that. Oh, and now we get a QV comes in, a QV. Well, what happens with this QV? So I'm going to try to do this your way. QV cross B, and so I get a force that goes that way. Well, what does it say that is going to happen? It says, looking from above, they both curve to the left. What can you say? Yeah, this is going to look correct. The same for you as for me. So this is curving to the right. But what if I put a negative sign in front of that Q? What if this was a negative charge? What would it do then? It would curve to the left. All right, so how can we make a positive charge also curve to the left? There's really only one way we can do that, and that is we have this QV come in here, and now, oh, yeah, that's positive. So QV cross B, force is that way, it's curving to the left. So the answer is the initial velocities were in opposite direction. And this will be true even if you kind of turn these so they're in a different angle. They still are both going to curve to the left if they're in the opposite direction. If that ended up being not clear, I'll take a look and see what you guys made of that problem. And I can see how that might be a little confusing, so I might make an accommodation there. I haven't graded the test yet. Okay. What would be a good reason to have power carried into your house with a cable containing two wires with current running in opposite direction? One current I1, one current I2. Matter of fact, let's just call it I1 and I1. Okay, the currents cancel out, so it's safer. Well, no, it isn't. If you put your hand on this wire, you would be in trouble. So, I mean, if these were bare wires, you could be in trouble. The currents cancel out so they don't create a magnetic field. Well, that wording was a little strange, and so you'll recall in class I just said the magnetic field created by these two currents cancel out. Okay, so that is true. And would that be a good thing? Yeah, that probably would be a good thing. You don't want a magnetic field in your house messing things up. So that would be a good reason for having the current run in opposite direction. Do the currents add so you get twice the power for free? No, doesn't work that way. All right. So, so the answer there is B. All right, number 8. Wire 1 carries a current of 20 amps. Wire 2 has no current. What happens when the current in wire 1 is doubled? I'm just going to remind you guys that mu0 over 2 pi r I1, I2 is the mathematical form of the force between two current carrying wires that are parallel to one another. And the question is, as a matter of fact, it doesn't even matter if these are parallel to one another. There might be a sine theta in here, where theta is the angle between these two wires, but it doesn't matter because I2 is equal to 0. So what you do to I1 is not going to do anything to the force. You cannot get this force to be non-zero because I2 equals 0. Okay, so what's the answer there? Oh, wire 1 has no effect on wire 2. That's letter C. All right. A current loop is in the xy plane. It is placed in a region of constant magnetic field in the z direction. All right, so this is what we have. We have something like this. Yeah, I just realized maybe my coordinate systems look not right-handed looking through the glass also. I'll have to check that. Okay, so what do we have? We have a current loop that's like this. And that means its magnetic moment here is mu, and we have a magnetic field in the z direction. So magnetic field is either this way or this way. So one of these is the magnetic field. Well, what are we being asked? We're asking if this loop is going to rotate or if this loop will feel a torque. Well, those are both the same question because it won't rotate if it doesn't feel a torque, and if it doesn't have a torque, it won't rotate. So what is torque? Torque is just mu cross B, which you guys will recall is mu B sine theta. And if this is parallel, if these are parallel or anti-parallel, then one way or another, sine theta is equal to 0. Therefore, there is no, does not begin to rotate, does not feel a torque. Therefore, it doesn't do both of them. Therefore, it's none of the above. But what if, and I'm going to cheat a little bit with my drawing here because, oh no, I don't have to cheat with my drawing. I thought I had drawn things in a way that it would. So now we have a B that's like this or like this. Well, now, what's the angle between mu and B? Mu B sine theta. Sine theta is now equal to 1. This is 90 degrees or 270 degrees, one way or the other. So mu B sine theta is just mu B, and so the loop begins to rotate and the loop feels a torque. So both A and B are correct for number 10. Okay, that's that for the multiple choice questions. See if I did less than 22 minutes. Woohoo!